Now we are going to discuss something called diffusion. Okay, so diffusion, the name, as the name implies, is about the species, like atoms, molecules, and so on, moving from one place to the other spatially within the material. Sometimes, maybe from one material to the other in other times. Okay, and before we move on and see what exactly is diffusion, what are their applications, let me quickly tell you the significance of this diffusion in any material, or especially for this engineering. Okay, so if you see the image there on the left hand side, okay, that is nothing but a small gear wheel where we want to transmit power, and the surface needs high hardness. Unfortunately, if you make this particular gear wheel with a material which is having very high hardness, the problem is it will or it may fail in a brittle manner, or abruptly, like just maybe broken into pieces. Okay, because once you apply load, maybe suddenly at one point it will break. Okay, so what I want is it should not be failing like in a brittle manner. That is why I use such materials where it's not just hardness, high hardness, it should be having sufficient toughness, ductility, and so on. But unfortunately, that if I choose a material which is not very having very high hardness, then the surface will suffer, right? It will quickly wear out, or change its shape, which should not occur. So what I can do, I can just modify the surface alone. Okay, I will make a wheel, something like this, or the gear wheel, and then with a material, I do make this wheel with a material which can withstand all the loads without failing, just abruptly, like in a brittle manner. Now what I try to do is, but this material is not having now sufficient hardness at the surface. So what I try to do is, I will increase the hardness only at the surface by, say, changing its chemical composition at the surface. Okay, and this is possible, okay, by different techniques. And all these techniques actually having the foundation on something called your ability to diffuse, okay, some other elements, because you want to alter the chemistry, right? You want to alter the chemistry by diffusing some other element. For example, if you assume this particular gear wheel is made up of iron or the steel, okay, then you can increase the carbon percentage by diffusing some carbon into the surface, so that you can increase the strength of the surface. Okay, and that is one application where you talk about the at what rate I can diffuse carbon into surface. How can I do that, what temperature should I do? All these things you can understand, provided you have the basic understanding of what is something called diffusion, and at what rate that happens in different materials. So to start with, you can understand the diffusion to be the net flux, okay, a movement of from one place to the other, okay, of any species, such as atoms, ions, electrons, and so on. Okay, and what are the two important things that actually determine or govern this particular magnitude of flux, is nothing but concentration gradient and the temperature. Okay, so we'll be seeing now, before we see about concentration gradient and the how do you model or quantify this particular diffusion itself in the material, let us quickly visit a small example, okay, to make you feel better, understand how the diffusion might take place. Okay, you take two pure pieces of copper and nickel and put side by side, okay, touching each other together. Of course, there should not be any oxide layers in between the copper and nickel, or any air gaps. And if you can maintain a bare bodies of nickel and copper touching each other, then actually what you could see is, with time, okay, there will be some diffusion that is taking place. That is, all the copper atoms at the interface, okay, may actually cross the interface. That is, some copper atoms move from copper side to the nickel, similarly some nickel atoms move from nickel to copper, and this is what will happen eventually. And now you can see the pure copper is only limited to on left hand side at the extreme left. Similarly, the pure nickel is limited to only the extreme right. So what could have happened in all other place? There is a combination of copper and nickel existing. Okay, how that was possible? By by way of diffusing, okay, like mass transport of copper and nickel into each other. Okay, and why it could have happened and why it should have happened. Okay, so all these things we can understand if you understand that if there is a concentration gradient, okay, there is always a possibility of migration of any of these species from higher concentration level to the lower concentration level, because that is a spontaneous thing to happen. Okay, because it will be settling at a lower free energy level. Okay, so without going further, so let us move on, try to understand what are the different types of diffusions that are possible to understand. So one you can call interdiffusion. That is what we have just seen, right? So interdiffusion is nothing but if your atoms are the species are moving from one material to the other material. Okay, then you can call it interdiffusion. It's only a name that you are giving. Similarly, self diffusion is also possible. You take only pure copper. Okay, is it possible for any copper atoms to move from one place to the other within the copper material? Yes, that is possible. Okay, for several reasons. Maybe the pressure gradient. Okay, so what happens now? You might be having for example some vacancy at some place, like we already know what is a vacancy, right? It is a point defect. So another atom, adjacent atom, might come and occupy this particular vacancy, right? So that is always on cards. So that is possible. That is what we call, okay, whatever the type of diffusion happening within the material, okay, not from one material to the other, then you can call it self diffusion. And another type of diffusion that we can call it as interstitial diffusion. As we all know, interstitial space is nothing but the space between the atoms when they are stacked together, and this space is always available, right? So if you have a small atom, okay, that can fit into this particular interstitial space of one particular atomic lattice, then this can always migrate from one interstitial space to the other, right? So that is what we call interstitial diffusion. And interestingly, what you can see here is if you want to see the self diffusion, where you need substitutional atoms, like one atom has to move and occupy the other vacancy position, but this can only happen if there is a vacancy, right? So these vacancy positions are the vacancy defects are all limited in number, though there are many, but they're still limited, right? In any material. Whereas if you see the interstitial diffusion, you can imagine the interstitial space to be available everywhere, right? So, because you will not be having a lattice structure or the crystal structure without having any interstitial space, right? So that is why we have a common understanding of the fact that the interstitial diffusion can occur more easily than vacancy diffusion, because vacancy diffusion you need the vacancy defect existing, right? So finally we came to a point where we want to now try to quantify, okay, the diffusion. Having understood the diffusion, what it is, and different types of diffusion. So now how do you quantify diffusion? Okay, I can quantify diffusion by using one thing is the concentration gradient, because that is what we believe is the driving force, okay, for any diffusion to take place. And what is this concentration gradient? If you have an imaginary a block of material, and if you assume the this is x-axis, and from one place, okay, in the x-axis, okay, to the other place, you can see here there can be a concentration gradient, assuming species having so much at point A and only this much at point B. That means this concentration gradient is there in the positive x direction, okay. And similarly, uh, if you want to quantify the rate of diffusion, there are different in fact two types of diffusions you can conceive. Okay, one can be steady state, the other one is the non-steady state. Steady state diffusion is nothing but where with time, okay, the rate of diffusion is not changing. Okay, whereas there can also be a possibility where with time the rate of diffusion is changing. Okay, quite possible, right? So if you assume there is always a time independent diffusion, okay, rate that is happening, okay, then how can you quantify it? By using this concentration gradient, as well as there is something else called, that is diffusivity. Okay, capital D, that is what I mentioned here. By the way, this equation is actually coined by Mr. Dr. Fick, who is a famous scientist, and we always call it Fick's law. Okay, who has worked a lot on the diffusion and its diffusion kinetics. In fact, he proposed a set of laws, okay, that govern the steady state diffusion and so on. So in this particular equation, what he talks about, or tries to estimate, is the constant flux that is existing, or the movement of species in a unit area, okay, across a unit area in unit time. Okay, so that value you will get if you know the diffusivity of the material and the concentration gradient. What is this diffusivity? Diffusivity is actually dependent on the temperature. Okay, you take aluminum, for example. Aluminum will have its own diffusivity at a particular temperature. Okay, similarly, if you increase the temperature, of course, obviously you are giving more and more energy to the atoms, and the diffusivity tends to increase exponentially. Okay, that's what this equation actually is trying to make out. So the simple thing here is, higher the temperature, more the diffusivity. That is why all these heat treatments, okay, are whatever case hardening that we just discussed, the surface hardening, okay, where you want to diffuse the atom into the surface to increase the or change the property. So you do usually all these things at higher temperatures too, in order to reduce the time taken for the species to diffuse from one place to the other, right? So and this is the final slide in the topic, which actually has a particular example that you can try, okay, on your own, direct application of what the formula that we just discussed. Okay, so with that, I hope you have a basic understanding on diffusion, what it is, what are the types of diffusion, okay, and how to quantify steady state diffusion, right?